Hi, welcome to R2E, and this is Meera Raman, and in this video we will talk about quantum field theory, right? So how one goes about doing quantum field theory is like you start with relativistic quantum mechanics and then you start moving on. That's one way of doing it. Do it. A historical way of doing it. How Dirac came up with things and blah. But what exactly quantum field theory means is that quantum field theory is nothing but it is quantum theory of fields. You have fields and you want to apply a quantum theory to it. So essentially what you are doing is field that is a continuous system, you want to discretize it. You want to create states in the fields of say some definite momentum, and somehow we don't have a notion of position in quantum fields that we will see later. But we'll talk about quantum field theory essentially. So what is a field? Field is something you have say some phi, and that is a function of x and t, and what happens is you define a domain where x belongs to some set of values and your t also belongs to some set of values, and your phi can take up all values for each x and t combination. That is in one dimension, and you can just put a vector out there and this essentially becomes 3-dimension and so on n dimensions. So those people who do some higher dimensional things like in string theory or other kind of things, we talk about physics where we talk about dimensions that are like more than 3. It's a little hard to understand, but anyways, okay. So yeah, this was it. So we'll start off with the how do you go about doing quantum field theory. Like, so what you do is you actually want to find phi which minimizes the action of the system. So in classical mechanics we have our action defined as s equal to integral L dt, and t goes from t1 to t2. And what the least action principle says is that the corresponding curve, that is your phi of t, that is your corresponding field configuration, your functional corresponding to this action, like something that you will see in configuration space, is such that your action is minimized. So if you take the variation of s, that's 0. So we call it as extremization of action. Now this extremization of action essentially leads to something very beautiful that we call as Euler Lagrange equation. Euler Lagrange equation. One of the most beautiful equations in the whole variational calculus, like something on which the whole variational calculus is based upon. So in today's video we will first derive Euler's Lagrange equation, and if time permits we will also apply it to a very simple Lagrangian that is called as the Klein-Gordon field, and we will try to get the differential equation of Klein-Gordon field from the Klein-Gordon field. Alright, so let's just first try some things out there, and we'll put some restrictions on what L is and what most other things are. Okay, so we have s equal to integral L dt from t1 to t2. Now what L can be? So L is generally a function of q dot t. This is, there is just one dimension I'm not taking the field, I'm just talking about a particle where q is your configuration space, generalized coordinate, and q dot is the time derivative of that. But I would rather encourage you guys to think of q and q dots as two independent variables. Okay, so this is it. And how do we go about talking about the least action principle? Is that you put your action, and there is L q dot t dt, and then you demand a variation in s. So that is from t1 to t2. So what will happen is, so you will take the variation with respect to q. So what will happen is you have del L upon del q, variation in q, plus del L upon del Q dot, variation in Q dot, and essentially time is something that you are varying. Time is your principal variable, Q1 Q dot R for the functions of time. I mean, we can just ignore that part. Okay, and there is dt. Now, I put a condition that at t1 and t2 at boundaries, my variation goes to 0. So what I'm trying to say is that suppose you have a curve here, and there are these 2 points in configuration space. So what happens is that suppose there is this curve on which your action is minimum. So what happens is all the curves that I will be talking about, all the variations that we're going to talk about is such that you have your curves here and here. But what happens is that variation, that these points, that this variation delta, it goes to 0 at the endpoints. So what I have demanded over there is that delta q goes to 0. How do I show that? But here I have delta q dot. So what will I do is, it's very simple, that I'll use the UV rule and I'll bring this the derivative of q dot over to this Lagrange part, this part of Lagrangian with respect to the derivative of q dot. So delta s will be integral 1 to t2, that will be del L upon del q, delta q minus of d upon dt of del L upon del q dot, and there will be del q. Okay, and yeah, it will be del q and dt plus boundary terms, let's say something like del q. Okay, just a second. Yeah, del q, del L upon del q dot, t1 and t2. Okay, so this is a boundary term. Like what I have done over here is that I have used the UV rule. So you have your UVV equal to UV minus of VDU. So what I just did was I had this thing over here, del L upon del Q dot, delta Q dot. So I take delta Q dot as my dV. I integrate it, so the dot goes away and it just it ends up with delta Q, del L upon del Q dot minus of, and what gets the V over there is your V simply will be this del Q, which is over here, and du has to be the time derivative of this quantity, this dot here. It's fine, it's so yeah, so this is still here the Euler. So okay, so this is still here, this is the mathematics part done. Now what we have demanded is that delta Q at T1 and T2 it goes to 0. Okay, so let me raise it a little bit and put these things in a little bit more space manner. Okay. Okay, so okay, so we have this thing over here. Now what happens is that T1 and T2 your delta Q goes to 0. So I am essentially left with delta S integral T1 to T2 delta Q del L upon del Q minus of d upon dt of del L upon del Q dot. Great, done. Now what we know is if this is extremized, delta Q should be 0. So here del L upon del Q minus of d upon dt of del L upon del Q dot equal to 0. And this equation is the famous Euler Lagrange equation. This one is famous Euler Lagrange equation. Okay, that's great. But you see till here that we haven't talked about fields anywhere at all. Your Q is solely a function of T. Q is what? Q is a generalized coordinate. in the configuration space. We haven't talked about that you have some sort of a functional, you have some sort of a field phi, right? And so that you can do variation on it, and you can like find a configuration of the field such that your action get minimized. What we have talked about? We have talked about that this will give me a path in the configuration space such that my action is minimized. But what about the field? So let's do this calculation again for a field. Now, the point to be noted is that the only difference between a field and a particle is that when you will talk about field, the field will be a function of x and t. Now, in x and t, it has to be a function of both. Like, x can be a vector, right? X can be x1, x2, x3, and you have t again. And if you go to the relativistic field theories, the status of all these four is same. So you can just put 1x, and that 1x means all four coordinates, correct? So let's just do a analysis for fields. Okay, great. So suppose I have a field phi and a function of x and t. Now what happens is, I define a Lagrangian, not Lagrangian actually, Lagrangian density, because this is a field now. So I define a Lagrangian density such that your Lagrangian is nothing but your x integral of your Lagrangian density, whatever, or that will be phi dot, phi dash, x and d. Let's see, there are like lot of terms out there. So your Lagrangian is a function of field itself, the time derivative of field, space derivative of field, space and time itself. Now what happens is, okay, so and this gives you Lagrangian, right? So your action should be integral dt t1 to t2 x. So what we normally do in field theories is that you integrate over all x. Now that question also gives, this statement also gives rise to the fact that whether there is convergence of the integral or not. It should be convergent most of the time, but sometimes there are things that happens. So that is dx. We have the Lagrangian phi dot, phi dash, x and t. Okay, now let's use the variational principles. So the variation of s. Now there is a thing about variation is s this time. So what happens is, in the case of particles, we demanded that variation vanishes at t1 and t2, like at times. But here what I demand is variation not only vanishes for t1 and t2 at the boundary, but it also vanishes for the boundaries of x's. Normally they are infinite, but if I consider the finite boundary, so they also vanishes at x1 and x2. Or you could also say that, like if x1 and x2 goes to infinity, you could also say that the variation vanishes at infinity. So there is no field and no field derivatives at infinity, which makes sense, physically which makes sense. Okay, so let's just do this again. So what we'll be left with is from t1 to t2 dt integral from x1 to x2. We'll have del L upon del phi plus del L upon del phi dot plus del L upon del phi dash, and that's it. Okay, this is all. Now again I'll use the UV rule, and I'll bring this time derivative over this phi term, this space derivative over this x term. So I'll again do that, and there will be boundary terms, and then boundary terms will go to 0 simply. So we'll have from t1 to t2 dt from x1 to x2 dx. We'll have del L upon del phi, like this, del phi plus sorry, not plus, minus d upon dt of del L upon del phi dot minus of d upon dx of del L upon dash. So this is it. Now for the again also you have this delta phi, you have delta phi terms over there. For this action to vanish, you will have this term, your del L del phi minus of d upon dt of, so del L upon del phi dot minus of d upon dx of del L upon del phi dash. So this is the Euler Lagrange equation for a field, which is fine, completely fine. We took the Lagrangian to have up to first space derivatives, but if you study field theories with a little bit more carefully, and you study something like the Lagrangian of the biological membranes, the cell membranes. So people do stuff on biological membranes, on the cell membranes. So there this Lagrangian completely changes, because you see, I should clean this stuff over here. So I got this Euler Lagrange equation, which is precisely what I wanted to do in this video, but a few comments and then we will end. So yeah, so what is the first thing is, all higher derivatives are also allowed. All higher derivatives are also allowed. So you can have higher derivatives like second derivative, third derivative, so and so on. And what happens is, like if you think of a membrane, or if you go to talk about something like continuum mechanics, and you do continuum mechanics, that is mechanics of solids, you talk about things like elasticity and something like, not sure about fluids, but yeah, for solids, you always have a, like if you have a beam and you bend it, then definitely by intuition you know that bending leads to energy, right? Some sort of energy has to be there. Like if you bend something, some sort of energy gets stored, so that as soon as you remove your hand or whatever the applied force, it gets restored back into its original position. So bending has to do something with curvature. Bending has something to do with the curvature. And for all those people who know a little bit of differential geometry, they know that curvature is nothing but is second derivative. Like if you talk about some surface phi, then its second derivative is actually it gives you the idea about the curvature of that surface. So if you are talking about biological membranes, or if you talk about solids, then your Lagrangian is out to have the second derivative, because if your Lagrangian does not have a second derivative, then you are essentially not talking about the bending of the membrane or bending of that solid. So this is what we have done, this analysis. This is up to first derivatives, and what will happen is, in the conventional condensed matter physics or in the conventional higher energy physics, you will never ever encounter some derivatives that are higher than the first derivatives. In cases you will definitely have the second derivatives. So what you should do in that case is that, like, you do the whole analysis, that what we have done right now, and you demand this variation vanishes, and then you also do things like, not just the variation vanishes, but the higher derivatives of variation also vanishes, and then you bring down that derivatives into these quantities. Like you have a second derivative term, and then you have probably d squared by dx squared, something like that, for a biological membrane. And like you can also have like other kind of derivatives here, and you can also always incorporate them into your new Euler Lagrange equation by taking the variation of the action, starting from the first principle and going back till here. So this was it, and probably in the next video what we'll do is, we'll take up a very simple action that is of a Klein-Gordon field, and then we will try to get to the Klein-Gordon field equations. And till then, I hope you enjoyed the video, and see you in the next video.